this lecture, we're going to learn how to quantify peak stormwater flows using the rational method. So within a relatively small drainage basin, so something smaller than 200 acres, if it rains with a relatively constant intensity measured by inches of rain per hour for a long enough period of time to generate steady runoff at an outlet or at another point of interest within the drainage basin, then the peak runoff rate will be proportional to rainfall intensity multiplied by the area of the drainage basin. This proportionality can be explained by a constant, which is known as the runoff coefficient. The rational method utilizes this runoff coefficient to estimate peak stormwater flow rates of stormwater runoff from small urban drainage areas. The following assumptions are made when the rational method is used. The first assumption is that the time of concentration for the drainage area is less than the duration of rainfall intensity. Also, that the rainfall intensity is relatively constant throughout, and that there's no storage runoff within the drain. The equation used to predict the peak runoff flow rate is Q equals CIA. So Q equals CIA to predict the peak runoff rate. Therefore, the required inputs for this equation are the assumed runoff coefficient, the average rainfall intensity, I, and the drainage area, A. Start with the runoff coefficient. The coefficient is based on the land use category within the overall drainage area, as shown in Table 1. So for example, if we have a grassy lawn with sandy soil, that would equate to a CQ value of 0.10. If we have something more pervious, like a roof, conventional roof, or a paved asphalt, those have higher C values of 0.85. So in general, surfaces that are more impervious have higher C values than surfaces that are more pervious. And when we install infrastructure like bioswales and permanent pavement and rooftop gardens, we're generally slowing down the flow of runoff from the site. And usually we're doing this by changing surfaces that are currently impervious into new surfaces that are pervious. So let's look at an example problem. Let's consider the following site of the Children's Center at SDSU. Right, so let's say that the site is delineated by this red line boundary here. And we can see that we've got a parking area, we've got some roof areas, we've got some green areas, and some wooded areas on the edge. And if we were to break down the total amount of area for each of these types, right, we can measure actually that 1.1 acres of that area is paved asphalt. And that gets a runoff coefficient C of 0.85. Approximately 0.7 acres on the site consist of roofs, which also have a runoff coefficient of 0.85. An area of 0.3 acres in this parcel consists of wooded zone, which has a runoff coefficient of 0.15. And then the remainder of the area on the site includes lawns with heavy soil, and landscaping with mulch. And those have runoff coefficients of 0.2. So once we determine the runoff coefficients, the next step is to calculate the rainfall intensity. So the way that we do this is by using intensity, duration, frequency curves. These curves are specific to the region where your site is located. And IDF curves, as they're called, the data can be found for anywhere in the United States from the following website published by NOAA. And this is an example of what one of those IDF graphs look like. So on the y-axis here, you've got the precipitation intensity, how hard raining, number of inches per hour. And on the x-axis here, you've got the duration of the rain event. So you can see that for short rain events, the intensity can be much higher, and the sustained intensity for longer rain events is much lower. We can also characterize rain events based on their recurrence interval or their average recurrence interval, which is also known as the return period. So a 1-year storm would be a storm that on average happens every 1 year. A 2-year storm would happen every 2 years. A 5-year storm is one that happens every 5 years. The 100-year storm is one that happens once in 100 years on average. So these are terminologies that we use to refer to storm events and their duration and their precipitation intensity. So let's suppose that we're looking at a 25-year storm with a duration of 60 minutes. We would read off the graph here and find that the rainfall intensity for a 25-year storm duration of 60 minutes is equal to 1 inch per hour. Right, so that would be the value of I that we could use in the equation if this was our design storm and if this was our duration. So how do we determine an appropriate duration to use in this equation? One way we can do this is by determining the time of concentration. So this is the time required for water to travel from the hydraulically most distant point in the basin to a point of interest, such as an inlet, and it's sometimes referred to as the inlet time. There's really no practical way of measuring this. However, we can conceptualize it as the sum of 3 different types of flow: sheet flow or overland flow. This is as the rain starts to gather in an area and it's kind of flowing over the surface as a sheet. Eventually, it'll start concentrating in channels, swales, and low elevation points. So we call that concentrated flow. And we can also distinguish that from flow in stormwater pipes or conduits. In urban areas, it's sometimes assumed that the time of concentration is equal to 5 minutes on approximately 5 minutes for roofs and paved stormwater intakes. And for other small areas less than 1 acre, it's often assumed that TC is equal to about 10 minutes. Right, so these are rough estimates of the time of concentration. However, there are more detailed methods that can be used to estimate time of concentration. For example, these tables and charts come from the U.S. Department of Agriculture Technical Release 55, entitled Urban Hydrology for Small Watersheds. So we're going to see how these tables and this chart can be applied in a step-by-step process to determine the time of concentration. So let's suppose that we have a grassy area as shown here in the photo. So if we're going to look at the hydraulically most distant point, it would be the point that takes the longest amount of time for one droplet of rain to make its way from that point all the way to the outlet. So it's not necessarily the furthest point away from the outlet. However, it sometimes is, but it's the hydraulically most distant point. So let's suppose that a droplet of rain falls here on point A and it moves down to point B via sheet flow. Right, so we have this segment ID AB, which we are having sheet flow run over the surface, which is characterized as dense grass. In table 3.1, we can look up the roughness coefficient of that surface of dense grasses, and we find that the value is equal to 0.24. Right, so that's called our Manning's roughness coefficient, N, and for dense grass, it's equal to 0.24. The next thing we want to look at is the length of flow. So let's suppose that the distance between point A and point B is 100 feet. All right, the next step is to find the 2-year 24-hour rainfall quantity in inches, which we can look up from the same source as the IDF curve charts, that website from NOAA. And we can find that the rainfall is 3.6 inches. So let's suppose for this particular region. The next thing is the slope. So we need to know what is the slope of the land from point A to point B, and that's usually expressed in feet per feet. So if we have a slope where the ground level drops by 1 foot every 100 feet, that would be 1/100, or a slope of 0.01. The last step, number 6, for sheet flow is to calculate the time of concentration for this segment, which is calculated using the equation shown here, 0.007 times NL raised to the 0.8 divided by P2, which is the 2-year 24-hour rainfall, raised to the 0.5 multiplied by the slope of the land raised to the 0.4. All right, and we would find that that is equal to 0.3 hours. So after sheet flow, let's suppose that the water hits sort of a natural channel in the grass, and from point B to point C, it is moving in shallow concentrated flow. So here we can use the graph shown here on the bottom left to find the average flow velocity based on the length of flow, the surface description, and the slope. So here you see we have an unpaved surface, and this chart only breaks it down between paved and unpaved. So here we have unpaved. Our flow length, let's say from B to C, is a distance of 1,400 feet. The watercourse slope would be the slope from point B to point C. Let's suppose that that's also equal to 1% or 0.01. And using the figure here on the bottom left, we can find the average velocity. So starting with the watercourse slope of 0.01, we're going to read off the graph until we hit the diagonal line for unpaved, because this is an unpaved zone. And then we would find the corresponding average velocity, which is equal to 1.6 feet per second. Last, we use the equation T equals L over 3,600 times V to find the time of concentration based on that length and that average velocity. And we'll find here that it's equal to 0.24 hours. All right, so far, it has taken our drop of water 0.3 hours plus 0.24 hours, a total of 0.54 hours to travel from point A to point B to point C. Now let's suppose that at point C, the water enters a field drain, at which point it goes into a stormwater drainage pipe system, and the last segment, C to D, is the water is moving in what we would call channel flow, where we can determine the flow length and the velocity using Manning's equation. And using that length and velocity, we can calculate the time of concentration, which in this particular example gives a value of 0.99 hours. So the last step would be to sum together these 3 parts to get the total time of concentration, which we can see here is approximately 1.5 hours. So let's do the example with our children's center site. All right, and let's suppose that the hydraulically most distant point is starting at point A over here. So we've got the first segment, which is from A to B. That would be sheet flow as it moves down that wooded area. The next segment from B to C is shallow concentrated flow on the asphalt parking lot. At point C, the stormwater runoff enters a drainage basin and is then conveyed to point D using piped flow, open channel pipe flow. All right, so let's fill out our time of concentration worksheet. All right, the first segment is segment AB. We can describe that as wooded area with light underbrush, which gets an N value of 0.4 for the Manning's roughness coefficient. The total length of this segment is measured to be 50 feet. If we look up the precipitation amount for a 2-year storm with a 24-hour duration in this particular part of San Diego, we find that it's equal to 1.95 inches. So that's our value of P2, 1.95 inches. Let's assume that the land slope is 1 foot drop for every 10 feet, which is 0.1. And now by plugging all those values into the equation in step 6 here, we can find that T sub T is equal to 0.14 hours. So now let's look at segment BC. So this surface is paved and it has a flow length of 370 feet. And let's assume it has a slope of 1% or 1 foot per every 100 foot. Using the graph here, bottom left, we can see for a slope of 0.01 and paved surface, we can see that the average velocity is equal to 2 feet per second. All right, so that's our velocity. We have our length. Using the length and the speed, we can determine the amount of time, which we can find here is equal to 0.05. So even though this segment is longer than AB, physically longer, it takes the water more time to move from point A to point B than it does to move from point B to point C. Right, and at point C, it then enters the drainage basin, and in which point it starts moving through the sanitary or the storm sewer pipes with open channel flow. So in this segment CD, and the same is true for your homework, you can assume that the velocity in your pipe flow is approximately equal to 3 feet per second. All right, so you don't have to go through the Manning's equation calculation shown here on line 17, which requires knowledge of the cross-sectional area flow, the wetted perimeter, the hydraulic radius, and we're just going to assume that the velocity is approximately equal to 3 feet per second, which is usually fairly close to what you would find in most open channel conduits. Length measured on the map from the previous slide is 120 feet. This gives us a travel time of 0.01 hours. So again, very small relative to that first segment with sheet flow. But nevertheless, we add up all these 3 different components and we can see that the total time of concentration is equal to 0.2 hours, which is equivalent to approximately 12 minutes. All right, so knowing that we have a 12-minute time of concentration, what is the rainfall intensity for a 10-year storm with a duration of 12 minutes? So let's assume that our design storm is the 10-year storm and our time of concentration was 12 minutes. So let's assume that we want to find the intensity for a storm with a duration of at least 12 minutes. We can see here that we have 10 minutes and 15 minutes. We can sort of interpolate and perhaps just round it to approximately 2 inches per hour. Now that we have all of our values and we've determined the land area and the associated runoff coefficient, we can use the equations Q equals CIA to calculate the peak discharge runoff, the peak runoff flow rate. Right, so in this case, since we have multiple land use types with different runoff coefficients, we have to add those different terms of C times A. We have to add those together as a summation. So that's why the equation is shown a little bit differently here, that Q is equal to I multiplied by the sum of C times A. All right, so I is equal to 2 inches per hour. That's our intensity. And then the sum of all C times A values is shown here, 1.1 acre with a C value of 0.85. That's the paved area. We have our roofs, which are 0.7 acres with a C value of 0.85, followed by the wooded area, 0.3 acres, the lawn, 0.1 acres, and the landscaped area, 0.1 acres. And this equals a total of 3.23 acre inches per hour, which we can convert acre inches into the more common units of gallons to find 87,707 gallons per hour. Now you should note that if you were to implement some changes in this site to change the area of land use types to different land uses that have lower runoff coefficients, then the effect will be decreasing the peak runoff flow rate. So that's really the topic of the assignment, is really look and see, which one of these land use types can we perhaps replace with something a little bit more sustainable. So the first culprit would usually be the paved area, asphalt. So you might look at your parking areas and think, well, maybe we can use paved bricks, brick pavers, which are porous and they allow the rainwater to soak into the soil a little bit. Maybe we can use those instead of paved asphalt, which has a much higher runoff coefficient. All right, so that would be your task. And pavers is just one option. There are many more green infrastructure solutions like bioswales and rooftop gardens and a number of other structures that you can implement and land uses that you can implement to decrease the peak runoff flow rate.